Okay, so welcome back to our second video in the Laplace transform unit, where we will finally get to see how this is going to be useful for solving ODEs, which we'll do a couple examples of in this video and some more next week. So just a quick reminder of what our main character is defined to be. So this idea of this Laplace transform formally is described or given by this definition here. So if you have some function little f and you want to do the Laplace transform of that, which is denoted with a script dl, if you sort of want to do a verb, I'm transforming little f, the notation we'll use for the transform after it's done is usually big F. And since s is the variable for the transform, because we're going to sort of a different, we're sort of transforming it in a different system, I guess, or a different world, s is the variable, and it's defined by this. Of course, this is an integral, where the little f that you started with goes here. And then the e to the negative st is basically what the transformation is, is how the function is being transformed. It's a little hard to see this in any real, looking at this definition, it's hard to kind of make sense of, so what is this doing exactly? And that's all right for now. But the word transform, at least, should hopefully, just as it means in English, I'm transforming it into an equivalent or alternate version. So actually, really, translation would be in some sense a better word. The Laplace translation might even be a better word, because essentially that's all we're doing with this, is we're going to take a function little f, we're going to translate it or transform it into a different language almost. We're going to work to find a solution in that other language and then translate it back at the end. So really, actually, natural human languages, I start with the problem in English, I translate it into Spanish, where for whatever reason it's easier to solve. I get a solution in Spanish, and then my very last step is going to be translate it back to English. So that's literally what we're going to be doing here, is the same idea of doing a translation or transformation. And this is how we're going to transform our anything, right? Any piece of our ODE is via this transformation. Okay, so in the last video we did a couple simple examples. We did this one, how to do a constant. We did how to do e, the exponential function, because that seems like that's a famous function that we encounter quite often, so we know how to do the transform of that. I stated these, I think, towards the end of the last video, Laplace transform of our two main trig functions, cosine and sine, and then a polynomial, right, t to the, or at least t to the n. How would you do a transform of that? And I think I made a little bit of a guess. I think I can erase, well, it's not going to let me erase, but my little asterisk turns out was right. I wasn't totally sure of what that one was, but that was correct. So these are sort of like our building blocks of functions. Of most functions are usually, have e stuff in them. They might have trig stuff in them, and they might have polynomial stuff in them. Those are our three main areas. So in some sense, while this is not a complete library, those are the big guns, right? Those are the main functions that we encounter in everyday math problems. So at least we know how to do the transforms of those characters. And I think I alluded to last time that there was a chart. So actually, let me flip over for a second here. So if you go onto Canvas and look, I think it's right below our videos for this week, there's a link there you see for what's called a Laplace chart. And it's just a chart that I made. If you Google Laplace chart, you're going to find a million charts that probably look almost the same as this one. But I figured I'd make a nice version of it for everybody. So if you open that document, which you're welcome to do so, you get this. One thing I would say is that if you want to print this, if you have a functioning printer at home and can figure out how to actually send print jobs to it. I have like 3 printers in my house, and I don't think I can actually send jobs to any of them, but if you do, and you can, you may want to print this, right? So of course, if we were together in class, I would be passing this out to you right now. because this is a handy reference chart that you're going to use dozens, if not hundreds of times in these in the next few weeks. So go ahead and, it's worth the ink to maybe print one of these off, but it's fine. You can always just look at it on your screen or in Canvas if you need to. What's here? So let me point at some things that look familiar, and then also point at things that don't look familiar yet. First things first. These first five. Oh, I'm sorry. So first of all, what is this chart? So this chart in the left column, these are functions. There's everyday functions that we see and that we use. And in the right side of the chart, as you can see here, it says big F of S. These are the transforms of these guys. All right? So this is going to be a very nice and easy, and in fact, the preferred way of doing a transform, again, unless I'm forcing you to do one, which I'm sure I will, on the next exam by hand, 99% of the time, right, in all other situations, don't bust out an integral to do these transforms. Just look them up in the chart. Okay? So the first five, these are the five that we did, or at least introduced, in the video, in the last video, and that I just recapped for you. A constant, E, polynomial, and then our two main trig functions. So the good news is those transforms are sitting right here for you. We'll talk about these a little bit later. These are, as you can see, combining E with these guys, basically, and how does that turn out? These 9, 10, 11, unless you know some more stuff than you should at this point, you don't really even know what UC and this, what's called a delta function is. So those are things to come. Those are physics things. So we'll get to those as well. But I do want to call your attention to the very bottom of the list. Oh, sorry, I don't know why that's blinking there. Let's move that over there. So the last three in the list here are three things that I wrote down at the very end of the last video. So number one, I wanted to point out to you, they're also in the chart, so they're right here for you. But just as a reminder, what were the last three things that I wrote down in the last video was in trying to move us towards a strategy for dealing with ODEs. Who else do we see in ODEs? Well, we see these guys, right? We see the the E's and the T's and we see those. But we also see these three guys, right? These y and y prime and y double prime are most certainly an integral part of ODEs. So if I have any hope, I know I haven't introduced the full story of how we're going to use these to solve ODEs, but at least at this point, just trying to get familiar with the vocabulary, I know that ODEs have these guys, these characters. So it would be nice if I could say something, or if I knew something about how would I do the Laplace transform of these three. So just to recap, the Laplace transform of y, remember, of course, we're solving ODEs, so y is our mystery unknown function, right? That's the solution to the ODE. So what would I say about the Laplace transform of y? Well, this is my smartass answer. It's the Laplace of y. Well, okay, because it is. All right, so that's not particularly exciting or interesting. But I did this one for you at the end of the video, 13, that if you have y prime, the transform of that actually gives you actually get s times the Laplace of y, minus y of 0, where, of course, y of 0 is our initial value, right? We were familiar with that from an ODE. And I didn't do 14, the last one, but it follows in the similar logic of what we did for 13. Y double prime turns into s squared times the Laplace of y minus s times y of 0 minus y prime of 0. Again, these are our initial points here. Okay, so number one, we love a chart, so this is great, and we're going to use the chart, like I said, extensively in order to compute transforms easily. And all our friends are here. All the things that we see in ODEs, and even next week, some new things that we don't even know what those are yet, are all here. So this is good news in the sense that I will have no trouble, and you really will have no trouble, computing Laplace transforms of stuff, because just use the chart. Right. But this becomes a silly exercise if I don't know what to do with those transforms that I've just computed. So this is the end of the last video. Sorry, I ended in a little bit of a weird place here because I really probably should have had that one on this slide since it's 1, 2, 3, right? But okay, whatever. So these are moving us though again towards how do I apply this to ODEs. So I'm going to give you the story, and I'll give it to you in two different formats on the next slide. Before I get to the story, I just have one last thing to note here, which is that the Laplace transform is what in math we call a linear operator. Meaning we have two properties, and you've seen these properties in a lot of operations that we've done in math. One, if you want to do, how do I handle coefficients? So I'll put a c in here. So if, let's say you have c times a coefficient, right? C is a coefficient, and you want to do the Laplace transform of that. Well, remember, of course, the Laplace transform is an integral, right? The definition of a Laplace transform says, hey, do an integral. And we all know very well by now that if you have a coefficient or a constant in an integral, you know you're allowed to pull that out in front. So of course, if I'm trying to do the Laplace of a number times a function, since it's just an integral, pull the number out and do the Laplace of the functional part, right? So if you like that notation, or if you like our S notation, same thing. All right, so this of course just says, hey, coefficients, no big deal. They just come along. So how many times have I said that to you in the last year or a year and a half, right? Because this is the same rule, same thing that we do with derivatives, and same thing we do with integrals, and probably a whole bunch of other stuff, right? Coefficients, no big deal, they just come along. Okay. And similarly, also, not a big deal, is what happens if you have more than one, and you're adding or subtracting. Well, again, I'll remind you, the Laplace transform is simply an integral, and we all know very well that if you have have a sum, if you have an integral of a sum of two functions, you could just as easily do the integral of each one separately and then add them up or subtract. Right? So this should be not surprising to anybody. That of course you could, if you have addition or subtraction, that's okay. Just do the Laplace on each term or each piece and then add or subtract accordingly. And again, if you're a big, if you like our big letter notation, right, that's big F plus or minus big G, I guess I would say, right? Little g turns into big G. Okay, so this is almost like a don't even think about this. Just do what your instincts tell you should be able to do when you have coefficients and more than one term. Now, it's not true for multiplication, right? I definitely couldn't say the Laplace of F times G is just the Laplace of F times the Laplace of G, right? That's not going to work. And you can probably, hopefully, you'd be able to see why that's crazy talk, right? Because you can't just do that with an integral. You can't just say, oh, well, I'll multiply. No, right? Okay, but for these guys, this is fine. Okay, so we're ready for our story now of how we're going to apply this. So using the Laplace transform to solve ODEs. Otherwise, I've just made up a random topic to fill the last 3 weeks of this semester. So how are we going to do this, right? How are we going to use our newfound tool and our newfound trick here to our benefit? Well, what's the idea, or what's the strategy? So of course I'll draw you, this is sort of the picture version of this. So on the one hand, we start with, as we have all semester, an ODE. And what does our ODE consist of? Maybe y's, maybe the derivative of y's. And what's the variable? T. Right? Y's, y primes, y double primes, and t. Right? So every ODE, we temporarily used x as a variable just for funsies, right? But I think we've mostly been using t as our variable. Okay, so this is just a regular run-of-the-mill ODE that we might have seen in the last couple of months. So we start here. Fine. Now, we know how to solve an awful lot of ODEs. So whether it's an ODE that we already know how to solve some other way, or some brand new ODEs, which we're going to eventually explore, if I want to try to use the Laplace transform to solve this, when might I do so, or what, and so what I might say is, well, either because I don't know how to solve this ODE, or maybe it's really messy, or things like that, I might have better luck if I translate it into an equivalent problem in a different language, right? Another good analogy is I'm trying to solve this problem on Earth, but for whatever reason, maybe it's easier to solve it on Mars. So I send the problem to Mars, I solve it there, and then I bring the solution back to Earth. I know it's a lame story, but that's what we're going to do with our ODE. We're going to say, hey, I'm starting with some ODE. I'm going to do, or you're going to do, the transform of each piece of every term. So in other words, we're going to translate or transform or translate our entire ODE into an equivalent ODE over here. So I'm going to have an equation over here. I'm not going to actually call it an ODE. I'm just going to call it, I would just call it an E. But I'll write that out, otherwise you're going to be like, what the hell is the E? So we're going to translate our ODE into what's actually going to just mostly look like an algebraic equation. And what's this going to have? Well, this is going to have, instead of y's, it's going to have Laplace of y's. And instead of t's, it's going to have s's. That always looks really funny when you write that, but you know what I mean, right? S's. Aha, okay. That should be believable, right? Everything that we've written down in the last day and a half-ish has said any Laplace transform we write down, the t's turn into s's, or we get an equivalent function with s, and y's turn into the Laplace of y's with some other stuff with some other s's. Okay, so it's at least feasible or believable that we're going to end up over here. Great. Now over here, I have an equivalent equation to the one that the ODE I started with. But what am I supposed to do with it? Well, the whole goal of doing this is to say that over here, again, on the moon, or in Spanish, or whatever analogy we want to use, allegedly somehow, we have to see this in action to believe it, but allegedly over here, I think I'm going to be able to use algebra only to, I'll say, solve this equation. Okay, to solve this equation, what does that mean? And by this, we mean make it read Laplace of y equals stuff. Okay, so here's going to be some terms, right? So whatever you got here, terms with s's. Because again, right, I got that. So basically this is just going to be an organizational step over here on the right, where I'm just going to do some algebra. Now, of course, I should be really cute, and if we were in person, I'd have that wry smile on my face where I'm just like, it's just algebra. And you'd be like, oh boy, that probably means crazy things are going to happen. And that's true, right? So we will actually have some regular and superhuman algebra skills that we might have to employ here. But I'll show you examples of those. But anyway, we're going to do some rearranging and eventually make this equation, just rearranging stuff to say, oh, okay, so let me write it as Laplace of y equals some stuff. And of course, since this side in this world, all my s is my variable, this is going to have some terms that have numbers and s's in them. Okay, hopefully that sounds like a thing we might be able to do. Fine, okay, but, well, I was actually hoping for a solution to the ODE. Now, if I read this, though, to you, what does this say? This says the Laplace, or the transform, of your solution. Remember, right, y is the solution, right? The transform of your solution is this. And that's like good news, bad news. Good news, I at least said the words, your solution is, somewhere in that sentence. But bad news is I said Laplace of your solution is this stuff. So if I could just get rid of that Laplace thing, I could maybe have it read y equals, which of the hundreds of ODEs you've solved this semester, they've all ended with y equals, or started with, I guess I should say, y equals, right? So the last step, so this is sort of step 1, 2, 3 here. The last step is to say, let me see if I could go backwards. So I'm going to try to do what's called an inverse transform. And what will happen if I can do that? So first of all, if I try to go backwards, Laplace of y is going to turn into that is going to turn back into just regular y, or I'll put y of t here for emphasis. And of course, this is the solution to the original ODE. That's good news. I'll put an exclamation point there. That's a happy thing. So that's me doing, so the notation that we'll use, like we always do in math when we want to say inverse, is we'll put a little -1 exponent on something. So this is known as the inverse transform. And how are we going to do this is, of course, how do we do the transform is we use the chart. So I'll just put in parentheses here. You use the chart from left to right, right? So when we do what we might call the forward transform or the regular transform, that's us using that chart I just showed you and looking up something on the left column and then reading to the right of it to find the transform. Well, if I want to do the inverse, which is also known as maybe the reverse transform, I would simply use the chart, but rather than going left to right, I'm going to go right to left. Okay? So I'll show you this, of course, right? But if I do that, now I don't need the chart in order to say, hey, Laplace of y goes to y. Well, that's just notation. But what I do super need the chart for is this step, which is to take each of these terms and translate them and inverse transform them. Let me draw a little bit better here. Maybe actually let me just draw a bunch of arrows, sorry. So I'm going to have several terms. Why am I making my life harder? Let me do it this way. So several terms, right? So maybe I'll just pretend here for a minute I have 3 terms. I could do the inverse of each of these. And again, that's going to be me reading the chart from right to left this time. I'd end up with maybe something, something, and something. Oh, but if I throw them all together, that's the solution to the ODE. All right, I'm going to erase my squiggles here. All right, so this is the, I don't know, blueprint, I guess, or the map of the strategy. Okay, as usual, we're going to do lots of these, and maybe this doesn't make a whole lot of sense right now. But this is going to roughly be what we're going to try to do. Start with a problem in English, translate it into Spanish, rewrite it, I guess, right, or organize it better in Spanish, so that my only, and this is the solution in Spanish, you could say, is what I end up with over here. And then my last step is to go back to English, right? So translate back over, and that will be the solution to the ODE. It's a little bit magic, right? I mean, it's going to seem that way when we do some problems, especially like, oh gosh, this seems like all we did was algebra, and yet we solved an ODE. But the answer is going to be yes, absolutely. All right, so if you don't like my picture, which I'm not a big fan of, I'm not always a super huge fan of, how about I give this to you more in the, so what am I supposed to do thing? So let's call this maybe strategy for solving ODEs with Laplace. Okay, so step 1 is going to be to take the Laplace of both sides of the ODE. So I'm going to do a complete translation. Okay. That'll be easy. That's going to almost always be just using the chart, reading the chart from left to right, and looking up the stuff that I have. Okay. Step 2 is to do my reorganization. So I'm going to rearrange the result so that it reads Laplace of y equals some stuff. Right? Maybe I'll say, let's pretend I have 3 terms. Okay, and of course we're going to do that just by algebra. We're going to get the Laplace of y terms on one side, the non-Laplace of y terms on the other side, then we're going to factor out the Laplace of y and divide the term to the other side. All right? So, but this will be, again, this is just algebra. This isn't too bad. Okay, so where's the bad step? Is pretty much the last step. So once I've gotten this rearrangement, right, so of course that's me down here in the lower right corner of our picture on the last one, I say, oh, okay, so Laplace of y equals this stuff. Well, the last thing I have to do is, in order to go back to our original world, is I have to take each of these terms, whatever I might have here, and I have to perform the inverse transform of each one. And by that, of course, I mean mostly I'm going to read the chart from right to left. So I'm going to look for these guys on the right side of the chart and then read off what's to the left of them. All right, so the last thing we're going to do is, I guess I'll say, perform the inverse transform of each term by doing the following. So since this is going to be the hard part, I'll try to give you a little bit of advice here. So first, which, I mean, we're going to use the chart for this, right? So I'll say by finding each piece in the right column of the chart. By right, of course, I mean right-hand side, not correct right. Right, so on the right side of the chart, try to hopefully find these, right? Whatever, I don't know what these squiggles mean, right? But whatever those things are, I'm going to be really happy if they happen to be things that are in the right side of my chart. Now, of course, right? Wry smile. Okay, sometimes they're not going to quite be in the right. They're going to maybe be close, and they're going to need a little bit of massaging. So hopefully we can find each piece in the right column of the chart. If it's not there, use algebra, manipulate it so that it does match. Okay, so this is going to be the annoying part, is that when you end up with stuff and it doesn't automatically translate, you have to do a little bit of creative algebra to make it turn into things that are in the chart. Okay, once you do that though, then of course read right to left to perform the inverse transform. I should say maybe of each term. And that gives you the solution. Okay? All right. So let's try this. I could talk to you for 10, 20 more minutes, but it's only going to make sense when we try some of these. So we'll try a few examples here. And I think you'll get the hang of the strategy at least. All right? So let's try. Let's start. We'll start with a nice easy one. So let's do, we won't even mess around with the second order. Let's just do a first order ODE. So y prime equals y, and y of 0 is 2. Okay, now conceivably this is a problem we did on the first day of the semester, back in January. And even if it wasn't one that we did one probably awful lot like it. And somebody told me way back when that a solution to this might be e to the t, because all this is saying is derivative of y equals y, which by now we're super experts in that. Oh, then we learn things like separation of variables. And I think when we solved this before, so I'm just going to put this in a little box over here on the right, I think we know from our previous solving capabilities that the solution to this is 2 e to the t. Okay, I'll let you have a nostalgic moment for a minute when you can look back to when we were all together in January, that this would have been a problem that we either did or certainly know how to solve already. Okay, so it's not going to be surprising if 5 minutes from now we end up with the solution of 2e to the t. In fact, it's going to be disappointing if we don't end up with that solution. But let's try this. Let's try this with our newfound strategy of doing a Laplace transform, and we'll see how it goes. All right, so let's try this Laplace-wise. So I'll try to number the steps at least to start here, as we're getting used to them. So step 1 is take the Laplace transform of both sides of the equation. Well, that's easy enough. I'm going to do the Laplace transform of y prime. I'll write this out very formally. And I'm going to do the Laplace transform of the right-hand side. Okay, now of course the Laplace of y is just Laplace of y, so there's nothing more to say about this. But this is the one we did in the last video, and or you could look that up in the chart in case you forget. That turns into s times Laplace of y minus y of 0, which is 2. All right? So that's, again, from the chart and or from our example that we derived last time. Laplace of y prime turns into that. Okay, so yay, we've successfully done step 1 of in our very first example. Step 2 says we're going to try to make this read Laplace of y equals, and then stuff. So the way to always do that is to get the Laplace of y terms on one side and get everybody else onto the other. So I'll move that guy to the left, and I'll move this guy to the right, and I end up with that. Okay, and then I want this to read Laplace of y equals, which means I should probably factor out a Laplace of y. And let's see what's left. S minus 1. Okay. And now in order to make this read Laplace of y equals, I probably just move that s minus 1 to the other side. Okay, and that's officially the end of step 2. So look how good we are. So we've made it read Laplace of y equals some stuff that has s's in it. Okay, and now we get to the sort of dreaded step 3. So we're here right now, right? We got Laplace of y equals some stuff. So to finish, I need to figure out a way to do the inverse transform of each term. Now in our problem right now, I only have one term, it's this. So my hope is that from using the chart, and maybe a little bit of algebra, I would be able to see this as the transform of something that's in the chart. So let's go to the chart very quickly here. And remember that, right? So I have 2 over s minus 1. That's what my goal is. So I'd be super happy if my chart had something like 2 over s minus 1 in it. But you can do a quick scan. And again, I'm looking on the right side of the chart now because I'm going to try to do the inverse transform. 2 over s minus 1, well, I don't see that anywhere. So this is where we're going to have to sort of do the, what's the closest thing that I have to 2 over s minus 1? Now, we're going to get better with this. But numbers are not a problem. Numbers, you can fudge numbers as you need. The s, the variable, that's got to probably be just about right. So we're trying to find 2 over s minus 1. If I could just find something over s minus 1, I'd be pretty happy. And that's where hopefully your eyes are going to go right here to the second rule, which says if you had 1 over s minus any whatever number you want, that when you go backwards, that turns into e to that number, t. Oh, okay, so let's remember this one, right? So if I could do 1 over s minus somebody, that would be e to the somebody t. Okay. So I look at this and say, ooh, I'd prefer to have a 1 up there. And that's where I say to myself, oh, well, all right. Oh, sorry, so I'm doing step 3 now. I say, well, I'm noticing that is in my chart. And then I'm saying, oh, but that's basically what I have. It's just that I have 2 times that. Right? That's what that is, for sure. Oh, well, now this is starting to look pretty good, because now I think in order to go backwards, first of all, I already did a little preview here. I know that the inverse transform of that, according to rule number 2, you don't have to put the rule numbers, but I'm just doing it here for your benefit, that from the chart rule number 2 says the inverse of 1 over s minus 1 is e to the t. We already discussed today, coefficients just come along. That works in forwards or backwards, right? So there's no, right, because again, these are just integrals. Right? So the 2 just come, the 2 in front there just comes along. And the inverse of, right, the Laplace inverse of the Laplace just gives you the original function again. Oh, and look at that. It's the same solution that we knew 5 minutes ago was the answer. But that's good, right? This newfangled way of solving ODEs, it's always kind of nice to check one that you already know what the answer is, so you can be like, well, does this seem like total crap? Well, we got the same answer that we anticipated. So before we go on and do another one, I'll just say, not that this is something that's keeping you up at night, I don't think, but it does seem a little bit like, again, we've managed to somehow solve an ODE, which we know usually involves calculus and integrals and, stuff. The only math I did here was algebra, right? I mean, and I used a chart. So, of course, anytime you've ever used a chart for something, of course, yes, the whole point of that is that probably the hard stuff is buried in there so you don't have to do it, which is great, right? But we are solving this thing. In fact, you can even see I used this initial value, and I used it early on, right? I used it in order to actually fill in my transform. But I did use it, and right, in fact, you could sort of see that the 2 just sort of travels all along here, right? And what's nice about this is that how did we solve this one way back when, is we solved it generically, and then we ran this through and figured out that the c that was here was 2. But you don't have to do that for Laplace. With Laplace, you don't have to, at the end, say, okay, now let me plug in the initial. No, it's just already there for you. So it's actually kind of slick. Now, if I was solving this in real life, that one, I probably would have just done it with separation of variables instead of busting out Laplace transforms. But soon we're going to see ones that actually this is a preferred strategy, I think, over older ones. But let's again try, I'm just going to keep going with another example of, again, one that we, I think, probably already know how to solve in other formats. But let's see. So let's try this one. So let's try a second derivative. We'll get a little bit bold here. So y double prime plus 4y equals 0. So this is still a homogeneous. But now it's a second order ODE, so I probably will have my usual 2 initial values. So y of 0 equals 2, and maybe just to make our lives easier, how about we also say, and y prime of 0 is also 2. Just to make the math come out nice. Okay, so let's try this. So let's see if we can trace this through and see what we end up with. So step 1, I'm not going to do 1, 2, 3, but step 1, do the Laplace of the whole thing. So all right, so I'm going to do the Laplace of y double prime. Now when I do the Laplace of with a coefficient, remember the coefficient just comes out in front. So don't stress about that. If you have a coefficient, probably just pull it out in front. Now Laplace of y double prime, if you look in the chart, you'll see that the Laplace of y double prime is s squared times Laplace of y minus s times y of 0. I'll write it out for you just for one time. Minus y prime of 0. So that's the Laplace of, so these 3, that's in the chart. The Laplace of y double prime is that. Okay, so I have this plus 4 Laplace of y equals 0. Okay, but of course y of 0 is 2 and y prime of 0 is 2, so those are going to fill in here and here. All right, so let me fill those in. So I have s squared Laplace of y minus 2s minus 2 plus 4 Laplace of y equals 0. Okay, so that's sort of step 1. I did the forward transform of both sides of the ODE. Or I should say the Laplace of 0 is 0. I mean, that would be world's easiest exam question to ask you, because that should be super obvious. I'll just leave it there. Right, so if it's homogeneous and you have a 0 over here, the Laplace of 0 is just 0. Right? Okay, so here I am. So I'm ready to rewrite this to read Laplace of y equals. So I already have all the Laplace of y stuff on the left side. So if I had that, if I put together the Laplace of y terms, what do I have? I have s squared, and I have 4. And those guys I'm going to move to the other side. The negative 2s and negative 2, if I move those to the right, I get that. And now if I divide, I end up with Laplace of y equals, and I'm going to divide this to the right side. So I'd end up with 2 plus 2s over s squared plus 4. Okay, now here's where I'm going to have some thoughts, and I'm going to look at the chart, which we're going to do in a second. And I'm going to hope that I see this or something like this or something I could work with related to this. I'm kind of hoping I see this on the right-hand side of the chart. All right, so what do I have? 2 plus 2s over s squared plus 4. And again, mostly it's the s terms. And in particular, as we're going to get better and better at this, it's actually the denominator is mostly what I'm looking at to get right. And I can usually fix the numerator. So I'm really kind of hoping, So I'm really kind of hoping that I'm able to do, to find s squared plus 4. So let's see. So if I look at the chart, so I'm looking over here, I'm kind of hoping that on the bottom I see something that looks like s squared plus 4, and maybe after a little bit of searching, I look at these two. These both say on the bottom you could have s squared plus a squared, where a is some number. And if I do have s squared plus a squared, if I could make it so that I had an a, so if that's a squared, then that's the square root of that on top, and or if I could have an s on top, I'd have good candidates to be transformed backwards into sine and cosine. All right, so since you hopefully have a paper, or at least can maybe remember these briefly for a second here, I'm happy, I'll be very happy if I could have either or both of these two. Sorry, I don't mean to be giving a seizure. All right, either this one or this one. If I could have those guys be part of my life, I'd be very happy, because I know how to pull those back. All right, so the bottom is already good, but I have to do a little bit of work on the top. So here we are again. Here's our problem. So I'm going to give myself a little more space here. So I have 2, right? I have 2 plus 2s over s squared plus 4. Now, if you remember in the chart here, I had 2 versions of s squared plus a squared. One of them has an a on top, and one of them has an s on top. But notice neither of them has 2s plus, 2 plus 2s. In other words, neither of them lets me have a plus on top. In other words, I can't have 2 terms on top. So here's where you have to use a little bit of algebra instincts to say, well, if I'm not allowed to have more than one term on top, how about I divide it into 2 fractions? That would at least have each of them looking a little more like those guys. So my motivation for rewriting it is simply to try to do matching. So this would match better if I wrote it as 2 over s squared plus 4, and then 2s over s squared plus 4. Okay, and that's of course legal to do mathematically, so I shall do that. And I'm already in good shape, because the first one is a perfect match. Now the second one, as I'm trying to line it up with something that I see in the chart, I sort of am a little bit like, okay, the first one matches, this one was sine, right? The first one is sine and this one's cosine. Right, so sine of AT, this is me just sort of previewing the chart for you. That's sine, and that's cosine, right? So this one's going to be great. It matches everything, right? I have a squared, a is 2, and that's a squared, and it's perfect. Okay. Now this one over here, let's do a comparison. So I have s squared plus a squared. Okay, so a could be 2 for this. That's all right. S squared plus a squared. But on the top, I'm just supposed to have an s. I'm not supposed to have 2s. Okay, well, this is not a hard problem to solve. Just do what we did in the last one and say, well, you don't want a 2 there? Factor the 2 out in front. Because remember, coefficients are no big deal. I'm going to be able to just carry them along when I do my inverse or forward transform. So this piece is now going to be a perfect alignment with cosine. So I'm ready to do my big step. So I'm ready to do the inverse. If I do the inverse here, I get y. That's great. That's the solution. And if I do the inverse of this one, let's see. So the inverse of this one matches perfectly with sine. I don't remember the number, but I think that was number 4 in the chart. Right? It matches perfectly where a is 2. So this is going to turn into sine of 2t. Okay. And this one, when I do the inverse, that's rule number, I think it's 5, which says this turns into cosine of 2t. So that turns into cosine of 2t. And then I don't want to forget, I had a 2 here, though. And when I do a forwards or reverse transform, coefficients just come along. And that is the solution to this ODE. All right, sorry, this is just my little chart preview, or chart whatever. All right, so let's stare at this for a minute or two before we call it quits here. So again, I'll say all I did here was algebra, and that's 100% true. Okay, there's maybe a little, I mean, this wasn't a crazy trick of saying, well, gee, since you have nothing that lets you have a sum on the top, split it into 2 separate pieces. This one needed a little massaging to get it to match perfectly with the chart, and then I used the chart in the most basic way to do the inverse of these 2 pieces. Coefficients, no big deal, they come along, and here's my solution. Now this is one that the solution here should look a little familiar, in that when we solved second order ODEs, which is what we just did an exam on, we did this a different way, right? We did the r squared and the r and the all of that, and we got the roots, and then we had 3 cases, and blah, 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 and we did all that stuff. And then at the end of the problem, we got little y1 and little y2, and then we had to do c1 times little y1 plus c2 times little y2, and then we had to plug these in and solve for c1 and c2. But look, it actually just comes out all at once in this problem. I didn't have to at the end say, oh, now let me use these 2. I used them. In fact, I used them in step 1 to fill in my transform. So as soon as these numbers got introduced here and here, they were already incorporated into my eventual solution. So I do think it's actually kind of a little bit slick. And this is one where, I don't know, I could maybe make the case that this was easier than doing it the old way. Maybe yes, maybe no. I don't know, it probably depends on how you feel about using this chart, I guess. But let's call this one a tie, at least, that if I did this problem, or asked you to do this problem on the exam, I don't think you would have done it in any less space than what I needed in order to get this one done. So, okay, so, again, this is still a problem that we already knew the solution to. But we're going to, very soon, next week, have problems that we don't already know the solutions to, and that this Laplace transform business is going to actually be the only way that we're going to be able to come up with solutions to some of these problems. All right. Now, what's a little bit missing from this, so if this is our usual second order ODE, well, I did a little bit of an easy one for the first one because there was no y prime term. So, of course, I know that I might have that, in which case I might have a little more finagling to do. And in order to sort of fix some of these, right? What else was a little bit sort of missing from this is that when we did a lot of these, we had an E in front of these. So there's a couple other rules in the chart that we'll do a little bit of exploring with on Monday, or in Monday's video. And I'll remind you of a couple of algebra tricks from your past. They're going to help us sort of target those problems. But then we'll look, again, after that, we'll look ahead to some new kinds of things, this U business that's in the chart, and that sort of scripty delta thing that's in the chart. And if we have time, which hopefully we will before we're at the end of the semester, we'll actually come back to spring problems, the vibration problems, and use these newfound functions that we'll do next week in order to solve a richer class of spring vibrational problems. So, hopefully this was good. If there's eventually going to be some homework problems, I will probably put them up before the weekend, and watching this video should enable you to do at least some of the easy ones, but you may want to wait until next week to sort of fully sink your teeth into the first group of problems. But I have nothing new to tell you, at least strategically. I'm just going to show you, again, like I said, I'm going to show you a couple other algebra tricks. But they're tricks that you've seen before. So, okay, so good luck. And since it's Friday, we're probably, when you're listening to this, I'll say have a wonderful weekend, and I will talk to you next week.